So welcome back to the lecture. Today our topic is B-tree. But before we dive into the insertion and deletion procedure of B-tree, we will start understanding the application of B-tree and how the B-tree is actually the necessity of the B-tree was evolved, and then we will go to the exact insertion procedure of B-tree. It will be easier to realize. So, so we will start from this concept of magnetic disk. So this this one actually it's very uh, well known to all of you. The hard drive that you have in your machine. uh, Now why it is connected, why I have given this particular information in this slide, and how it is connected with B-tree, that you will realize automatically after some couple of slides. But before with that, let's start this point, that how a data is actually stored in a hard drive, something like a what we call magnetic disk. So one thing you remember, this according to this diagram that you find in the right hand side, this magnetic disk is actually a combination of many disks that have lot of spindles. That have a spindle something like this. Okay, and there is a lot of cylinders, a disc actually we have over here. This disc actually rotates. Okay, and there is a read write head that you find it over here. This is the actual image of a hard drive, and if you just open it, you will find the components of the hard drive is something like this. Now this is actually given as a diagram in this left hand side. So you can imagine that this is nothing but the read and write heads, and this is the arm. Actually this arm actually moves from here to here in this way, and this spindle moves in this direction. So naturally you will able to, this particular read write head can be able to read any data present in anywhere in the disk. Now how this particular disk is actually how the data is actually kept in this particular disk, to realize it, one thing first you remember, that data is kept in a particular block of a disk. And how this block is defined? This block is defined by two components. One is track number and another is sector number. Now question is that what is track? Track is actually something like this. This is one track, the outer circle. Every circle is a track. And in a similar way, the whole 360-degree disk, circle disk, is divided into many partitions, something like this that you can see over here. Now, a single partition as a whole is called a sector. So that means a block is nothing but a particular track of a particular sector, something like this as given over here, that this is, say, if you consider that this is track number 1, this is track number 2, then this is track number 3, track number 4 and track number 5, then you can say that the block that is given over here, shown over here, is nothing but, say, under track number 2, and obviously, like track number, we have a sector number also. Like if we consider this is sector number 1, then it is 2, then 3, then 4. That means track number 2, sector number 4 is this particular block. So any data is stored in a block, right? Now naturally this block is not only of one byte, it is of multiple bytes. I mean, you can assume that 2 to the power n bytes. Now obviously this n depends upon the size of the total disk, right? And the size of uh, the system, the memory of the system. So depending whatever the value of n, doesn't matter. For example, say 64 kilobyte. So you can consider that a particular block size is say 64 kilobyte. Now, uh, now obviously the data that you have is every time needs not of 64 kilobyte. It may be of only 1 byte. So in that case, that means the computer needs to traverse each and every bytes individually in a particular block, right? So we consider that with the, I mean, just would consider this particular block as a array of bytes. So it start from this address, says it is 0, then 1, then 2, something like this. Naturally, to reach to a particular byte of a particular block, you need something more which will specify the exact byte of the block, and that is what we call offset. So that mean uh, ultimately this byte address can be considered as a block number and an offset. Now naturally question will come that why we are talking about this. The reason is that we will start, as I told you, that we will start with the application of B tree, and how this we will start realizing that how this B tree was evolved. Always remember, this B tree is basically applied for what we call multi-level indexing. So naturally again question come that what is multi-level indexing. This multi-level indexing is actually highly required for storing a large number of files in a particular disk, especially in case of database management system. So this is what we have seen, exact vision how our data is stored, and this data can be in any form, and this data is actually suppose in a in a DBMS form. Now so natural question will come that, but before that, how DBMS work. So we have to understand that how this data is accessed by a computer, because one thing we know that a computer has different types of memory in our in its side, right? So that means if we consider that this is a whole computer system, and we know that we have a central processing unit which actually directly communicate with the RAM, right? So main memory, what we call main memory, and also we call RAM because this is a basically technology by which this I mean addressing is uh, addressing is done. But ultimately the large amount of data is not possible to store in RAM, right? And that's why hard disk is there. And this secondary memory is nothing but what we have seen over here. So this is the secondary memory that we have. And you see, when a data is required, which is present in the secondary memory, the central processing unit actually start requesting this data from this RAM, because the CPU can only communicate with RAM. CPU first request the data to the RAM, and if the data is found, then RAM directly send the data to the CPU. But if it is not found, then this RAM actually puts a request signal to the secondary memory storage. And if it is granted, then through some process of reply, the data is transferred to the RAM, and then it goes to the CPU. Something like this. Now naturally, we know that this secondary memory is very large. So if we don't have a proper data structure to store this data and keep track where the data is actually present, this RAM will take a lot of time just to search the data in a, I mean that means that to search the exact offset where the data is present. The offset, that is what we were discussing. So actually the RAM is required this location to identify this location, that where the data is present. But if we don't have an intelligent way to search it, to keep a track about the data, then it will be very difficult for the RAM to search a data in a say gigabyte and terabyte amount of memory location, right? And this is a situation where this indexing is required. Now, what is indexing, that we will come very soon, but before that, we will see that how, what is exactly, what is a DBMS, because ultimately we will try to realize this indexing from the DBMS point of view. You see, this by definition, we say that our database management system is a software designed to store, retrieve, define, and manage the data in a database. So one thing is clear, that this DBMS is basically related for storing and managing with the data. But where it is stored? It is stored in a database. So DBMS is a software and database is the actual storage. So naturally next question will come, that what is the database? That's why I have given the definition of database also, that a database is a organized collection of structured information or data typically stored electronically in a computer system for easy access and management. In this particular definition, one word is very vital, that is this one, structured. Now question is that what is structured, right? So that means all the data that we store in a computer are not structured. So how we can do this? You see, for example, in a very well-known, well-known environment we have, that is Facebook. We have lot of different type of way by which we can interact with this website. We can like a particular image, we can share some particular image or maybe video, or maybe we can comment something. Even in the comment I can write something, as well as I put some image and many more. So naturally question will come that this image, text, video, all are not similar type of data. They are different type of data, and how they are stored. Question is that how you can differentiate with the image and a text when you are storing. Obviously there is a server, Facebook server somewhere else. Whatever image that I am storing in the Facebook is basically stored in the image, the Facebook server somewhere, maybe in America or England, I don't know. And what is server? Server is basically a machine, a trillion, a billion amount of hard disk, right? Now those information we cannot say they are structured, because we have variety of way I can actually, a user can give the data to the Facebook server. Variety of way in the sense, the input can be text, the input can be an image, input can be a video, input can be any combination of this. So structured database means structured information mean there is a common way by which each and every data of the system is stored. And how we do this in a structured way in a database, that we will see in the next slide. But before that, since it is structured, and that is why there is a programming language for retrieving data or managing data in a database, that is what we call structured query language. Okay. So this structured query language is basically a query language, a programming language that works on DBMS. On some DBMS, there are a lot of different type of DBMS, maybe Oracle, maybe SQL Server, maybe IDM database, I mean IDM DB, and many more. Okay, so whatever the company doesn't matter, but the idea of DBMS is same for all, and idea of database is same for all. Maybe the structure is different, and the way of writing the SQL is different, but the basic idea of SQL is same for all. Now, naturally, next question will come that how we can store structured information in a database. We store structured information in a database in a form of table, something like this. So for example, if I want to create a database having the data about the students of this BIT, then basically we can assume that we have this amount of information about each student. So that means this is a particular information about a student. So assume that only this information I want to store. That the student's roll number, its name, its department, in which year he is or she is right now, and his or her contact number. So one by one I can put them in each and every row. So this is what we call table. In this table consists of multiple number of row, a number of rows and a number of columns, what we call attributes. And there is some interesting information in this table, that is, if you see that if I want to uniquely identify each and every record in a particular table, then which particular attribute or set of attributes you will take. For example, if you consider that I will try to identify each and every row by the attribute name, then your purpose is not going to solve, because there is no guarantee that there is no student having name Ronak or Wahab or Anurag or Annesha, whatever is there, having the same name in the college. You may have same name in other department or maybe in other year. So if I just want to find that the detailed information about Anurag, it's not possible to find out. There is no guarantee. Maybe I will find more than one row. Similarly for department, you cannot do that. If you consider CSE, lot of students from different year will come. Similar for year, similar for, that means there is only two things, that either roll number or contact. If you consider this roll number, you see if the name is same, department is same, even the year is same, then also the roll number will differ. So this attribute roll number is one of the attributes which can uniquely identify each and every row or the record in this table, and that is why this roll number is called unique, actually called primary key. So I'm not going, this is not a class of database management system, so I'm not going in detail of this, the detail of this particular, of the table. Just as, I've given you this information as a prerequisite to understand what is DBMS and table and all. So, but my goal is that, assume that we have 500 records over here, so the number of records is too large. If we consider we have a very limited amount of memory in my system, then question is that how we can store it, and especially how we can actually access each and every record of this particular uh, I mean in this part of the particular table. So you see that this particular image already we have seen in the previous slide, So suppose this is my hard disk and somewhere this particular table will get stored. Now question is that to store this table in this particular hard drive, how many blocks I required? Just arbitrarily, if I consider that the disk block size is 64 byte, okay, 64 byte means a particular block of a disk, this is which one in blue is 64 byte suppose, and the record size, that is the size of the particular row, each and every row is a 16 byte. For example, this is a 4 byte, this is 2 byte, 2 byte, 2 byte. So as a whole, a particular record will take 16 byte location to store. Then in a particular block, how many record you can store? Obviously 4, because total number of total amount, I mean size of this block is 64 byte, and a particular record will take only 4 bytes of data. I mean sorry, 16 bytes of data, bytes of location. That means total you can store in this particular block first 4. You can assume in this way. Next 4 require another block. Next 4 require another block in this way. So that means if I want to store these 500 records, how many blocks I required? I total require 500, I'm sorry, 125 blocks. Why? Because a particular block take 4, I mean a particular block contain only 4 record, and I want to store 500 records, so it will require 500 by 4, that is 125. It's very simple. So now question is that if the RAM want to find a particular record in this particular in this table of this table, what is the worst number of time, worst maximum number of block it has to check? In a worst case, you can say maximum number of block it has to check, that is 125, right? If I still consider a very bad searching algorithm, say linear search, right? Total 125 blocks it has to search. Naturally question will come that is it possible to minimize this number of searching? Obviously I want to do that, because as much as I will able to minimize the searching, the machine will become faster. So I mean it can be something like this, the first block somewhere here, second block, second 4 information somewhere here, something like this, and so on. So now this is our question, that can I reduce this? Yes, we can reduce this. How? With the help of this indexing. So now the indexing comes into the scenario. Now what is indexing? Just before we dive into what an indexing is, from the computer science point of view, you can easily try to realize it with the help of a practical example that you have. For example, in your book, whatever book you have, maybe a story book or anything else, suppose the book, the total number of pages 500, and you want to, there is say 20 different stories present in the 500 book. Now if you want to find a particular story, what do you do? Will you start finding the first page of the story from the first page of the book and you linearly check all the pages? We don't do that. What we do, we have an index where it is stored that this story number 1 page number N, story number 2 page number M, story number 3 page number P, something like this. So we find the story name from the index, and then accordingly we find corresponding page number and directly we go to the page number, instead of checking each and every page we do in this way. And this is what indexing is. So the same thing that actually we are going to apply over here. So that means we have a situation something like this, that we will not store, I mean obviously this table has to be stored somewhere, but the RAM will not search something from this table directly. We will have one more table, that is index. That table will contain this roll number and a corresponding address, and this address is nothing but the exact offset address of that particular block, of some particular block, which is connected to this table. So you can assume that this is nothing but a pointer. You can assume in this way that if I want to search, I mean when the RAM want to search a record having roll number, because roll number is a unique key that we have seen, you can easily uniquely identify a particular record by roll number. So assume that I have written a query that select everything from this table where roll number is 12100320045. So naturally this query will go, the processing, the CPU will, request this query to the RAM, and RAM will request the same query to the hard disk somehow. And in the hard disk, that means in that particular, circle structure of the disk, when the query come, the query will check in this table, not the right side table. No, it will check where this roll number present in this particular column. Whenever it will find out, it will find corresponding address, and this address directly redirect the system to the exact location of the record. So what benefit I will get? The benefit number one, we can easily understand this from the point of view of this simple mathematics. That is, I have a disk block size is 64K, that we know, right? And assume that this index size is 4 byte. Okay, so instead of 16 byte, this 4 byte is there in the index table. So now if I want to ask, naturally next question will come that where this table will stored. Like this particular table is getting stored in the hard disk, where this table is stored. This table is also stored in the hard disk. There is no, there is no doubt. So to minimize my searching, I am basically storing another table in the hard disk. Is it really a solution? Let's see. That assume that this index size is 4 byte. So if the index size is 4 byte, now natural, we have seen that in this particular table will take total 125 blocks. How many blocks this table will take? According to these two assumptions, I can say the number of blocks that is required to store these 500 indexes is 32, because index size is 4 byte. So naturally that means in a particular block, total number of indexes you can store is 16. That means 16 row you can basically store in a particular block. And if you are able to do that, that means to store these 500 indexes you require 32 blocks. right? So that means 32 blocks are occupied for this index table and 125 blocks are occupied by this for this actual table. So if I still consider that I have a linear search, the question will come that how many blocks I have to check. In a worst case scenario, I have to check 32 blocks for finding that particular roll number from the index table. And as soon as I will find that, due to this address, I am directly jumping to one of the block of this 125 block that is storing this table, right? Not all the blocks of the right? So that means total number of blocks that you are accessing is 32 plus 1. 32 in worst case for searching the roll number in the index table, and 1 is that. Why 1? Because as soon as you will get the roll number, you can directly go to the block according to this address. So naturally, total number of you can say the accessing of the index is 33. So initially in the previous case, when we didn't have this indexing, then um, how many searching was there? How many searching on block was there? 125 searching. And now it is minimized to 33. So we have conceived, we have converted the machine to much more faster, right? But still, we have a problem. Problem in the sense, it's not problem. The problem is that if the index table is itself very large, then what to do? For example, if I consider that we have a large number of index table. For example, we have 500 entries over here, right? If we consider I need 5,000 entries, then index table is also large. So in that case, is there any way to minimize much more? So that answer is actually the what we call multi-level indexing. Multi-level indexing. So now what is multi-level indexing? You can easily, guess the multi-level indexing from this name. Like we have index of indexes. That's in each and every level. So you can assume that this is level 1 index, and we will try to put one more indexing that will basically index of this level 1 index, and if required many more indexings. So a scenario is something like this, that in the right side we have this table, right? So this is the index table that we had, and in the right side we have the actual table that I have not shown you, that you know this. Now this table is suppose very large itself. So if this table is too large, then we can put it in a similar way. We can break the roll number into two parts. This was the actual index, right? Roll number. And now somehow I have broken the roll number into two parts. And this roll number part 1 is there, and according to that pointed to the index 1 is there. Something like this one. This is roll number part 2 pointed to this again, something like this. So in this way, we can actually form a multiple level of indexes to identify a particular block, something like this. So that means, what is this roll number part 1 and part 2? I mean, what I want to say, since I have taken these roll numbers in an arbitrary way, that's why it's not directly right now possible to show you that how it is being exactly divided into two parts. But in actual scenario, for example, somehow there is some number, for example, there is some number, and this has been divided into this half is this part 1 and other half is this part 2. So when the roll number, actually the query don't have any idea that roll number has given divided into two part. So when some user will give the query, he will put the roll number as a whole. The software will divide this roll number into two part. I mean, the software means who? The operating system will divide this roll number into two part, and according to that, the OS will start searching the particular roll number in this tree structure. You see, if you the structure that is formed over here, if you just invert in 90-degree, it is going to be a form of tree. And this is the basic idea from where the B tree came. But still, there is a lot of things to left. One by one, we will see that. So, this multi-level indexing is basically formed because of that the number of indexes in a particular level is going to be very high. And if it is very high, then we will divide this indexing into many more levels so that as a whole total searching time minimizes.